Today our goal is to use similar objects in 2 or 3 dimensions to compare ratios between side lengths, perimeters, areas, and volumes. Also to determine how changes in 1 or more dimensions of an object affect area and/or volume of the object, and how changes in area or volume affect dimensions. Also to be able to solve real-world problems about similar geometric objects. Recall that similar polygons have the same shape but different size. Therefore, the angles must be congruent and the sides must be proportional. Remember that when sides are proportional, there's a correspondence between the lengths such that when we make a ratio with the corresponding lengths, it creates a scale factor. The relationship between any corresponding lengths in similar polygons is that the ratio of any two corresponding lengths equals the scale factor. So you can take one side and put it over a corresponding side, and those lengths create a scale factor. But it doesn't have to just be the side. So any corresponding lengths, when we say any, that means the sides. That means the altitudes. That means adding up all the sides, which is the perimeters. Any corresponding lengths, put them over each other to make a ratio, and you get the scale factor. Let's take a look at an example with these two triangles. We are given here that triangle CAB is similar to triangle DEB. First, we're going to find the scale factor of triangle CAB to triangle DEB. So we need to match up corresponding lengths for the scale factor. So let's look in our picture to see where we have some numbers. In triangle ABC, side AC has a length. Altogether, that length is 12. AC from the statement corresponds to DE. DE has a length. Altogether, that side is 16. So I'm going to put 12 over 16 and simplify that ratio, 3 over 4. The scale factor is 3 to 4. Remember, there's different ways to write it. Also with the colon, both are acceptable. Notice that if we took just half of the side, since it looks like it's divided in half, 6 and 6 and 8 and 8, and use those corresponding lengths, like here and here, and 6 over 8, we reduce that ratio, it also reduces to 3 over 4, same as the scale factor. Remember, the ratio of any two corresponding lengths equals the scale factor. Let's look at the next one. Find the length of the altitude FB. So they want segment FB, this segment right here from F to B. Well, what is an altitude? We don't really need to know what an altitude is to do this problem, but we might as well discuss it here. Altitude means height. The height of something goes from the very top of it straight down to where the base is. Now, this one's going this way, so let's look at this by changing it, just turning it around. So they're calling it an altitude. That just means if we turn the triangle around from F to B, this segment right here is what we need to know. So we're looking for the height of the triangle if the triangle is turned this way, such that AC is its base. So that's going to be useful to us for what we're doing in part C. So we're trying to find the length of FB. What's the corresponding length in the other triangle? Well, from F to B, notice that B is the corresponding angle. So from B straight down to its base, as if we were able to turn this triangle also on its side. So if we can turn this triangle on its side, then we can see that that is the altitude also of the larger triangle. So let's make a proportion to find the length of FB. We know that FB corresponds with GB because they are in corresponding positions. So FB, which we don't know, over GB, which is 20, equals the scale factor. Remember the relationship, the ratio of any two corresponding lengths is equal to the scale factor. The scale factor, 3 over 4, and then we can cross multiply to solve. So 4 times FB equals 3 times 20, which is 60, dividing by 4, FB equals 15. There's the length of the altitude FB. Find and compare the areas of each triangle. The areas of the triangle. Now they give us a formula, area equals 1/2 base times height. That's why we need the altitude. H for height, and another way to say height is altitude. So in each triangle, we now have that. FB, the height in this one is 15. Here the height is 20. Earlier, we found the base by adding up that entire length. There's our base. B is for base. So let's do each area. Area of triangle ABC, 1/2. The length of the base is 12, and the height, the altitude, 15. Half of 12 is 6. 6 times 15, 75. Oops, excuse me, 90. I was doing 5 times 15. Okay, and then the area of triangle DEB, 1/2 times the base, 16, times the height, 20. So we have half of, I'll do this one this time, half of 20 is 10, and then 160. Now we found the areas, 90 and 160. Let's compare them, compare the areas. Well, how have we been comparing things so far? As ratios. Let's make a ratio out of these areas. 90 over 160. Let's simplify that. Divide by 10, get 9 over 16. What do you notice about these numbers? Think about how they compare to the scale factor 3 over 4. Have you thought of it yet? 9 is 3 squared. 16 is 4 squared. So if we're finding area, which is two-dimensional space, square units, we are using the scale factor squared to show the ratio of areas of similar figures. In fact, that's how we usually write the answer for area. If I had units in this picture, I would take my units and square them. 90 units squared, 160 units squared. Let's write down that relationship between the areas. The relationship between the scale factor and the area of similar figures. The ratio of the areas equals the scale factor squared, the square of the scale factor. How can we use that? Example 2, corresponding lengths in similar figures are given. Find the ratios, shaded to unshaded, that's just helping us remember to go from left to right, of the perimeters and the areas. Then find the unknown area. So first the ratio of the perimeters. So we have to remember perimeters is a length. If it's length, that's just the same as the scale factor. Area is two-dimension. If it's area, that's the same as the scale factor squared. So let's first find the scale factor. How do we do that? Match up the corresponding lengths. This side corresponds with this side. 14 over 20 gives us 7 over 10. That's our scale factor. Our scale factor from our corresponding lengths. Scale factor is 7 over 10, therefore the ratio of the perimeters is 7 over 10. If it's any type of length, it's the same ratio as the scale factor. How about the ratio of the areas? Scale factor gets squared. So 7 squared over 10 squared, 49 over 100. There's the ratio of the areas. Now we can use it to find the unknown area. We do that very similarly to how we find a missing length. In this one, the area we don't know. It's unknown. In this one, we know the area, 400 inches squared. So let's make a ratio out of unknown area to known area. Maybe we write A for area over the area that we know and the ratio that it's supposed to be equal to, 49 over 100. How do we solve a proportion? Cross multiply. Let's do it. 100A equals 49 times 400, and solving for A, 196 units are inches squared. So there's the unknown area. Let's look at another. Two similar cylinders have heights 4 inches and 6 inches. Those are the heights. Maybe we draw that in the picture. So the height from top to bottom, or the altitude, 4, and the height from top to bottom, or the altitude, is 6. We should put the units to remember that we have them. What is the ratio of their heights? So that's not bad. We've done that before. 1 over the other, 4 over 6, makes 2 over 3. That's the ratio. What is the scale factor? Same thing. Ratio of the heights is the same as the scale factor. What is the ratio of their surface areas? Well, what's surface area? Does it matter? I see the word area, and that's what's important. Any type of area means I take the scale factor and square it. So our scale factor is 2 over 3, square it. 2 squared, 3 squared, 4 over 9. There's the ratio of the surface areas. 4 over 9, it's a type of area, so we square the scale factor. Next, find the volume of each cylinder. Here's the formula for volume. Let's compute it. The volume of the first cylinder, volume sub 1, V sub 1, pi r squared h. So our first volume, pi, radius squared times height. The radius is this part, the radius from the center of the circular cylinder to the edge. So that's our radius right there, 2 squared. And then the height says 4. So 2 squared is 4, 4 times 4 is 16, and we'll just write 16 pi. These are inches, so inches cubed. Second volume, pi radius squared times height. Radius, well, it's not shown. It should be the part of the cylinder that's from the center to the edge. But what is that? Remember, corresponding lengths have the same ratio as what? The scale factor. And this scale factor is 2 to 3. So if this radius is 2 inches, this radius must be 3 inches. Those are corresponding lengths. So 3 inches and 6 inches. So let's square those. 9 times 6, 54. So 54 pi inches cubed. If we really want to bring out our calculator, we can do that, but there's no need for that computation. Find the volume of each cylinder. Done. What is the ratio of their volumes? Let's make a ratio. 16 pi over 54 pi. Now, the pi's can easily divide out. Let's reduce 16 and 54. 2 goes into 16 8 times. 54 goes into, or 2 goes into 54, excuse me, 27 times. So what does that look like? Well, remember how we wrote our volume units? Volume is three-dimensional, so inches cubed. That's what we do with our scale factor. 8 is 2 cubed. 27, guess what that is? 3 cubed. 2 cubed and 3 cubed. So there we can write now the ratio of the volumes, the relationship between the scale factor and the volume of similar objects, the ratio of the volumes equals the scale factor cubed. Let's take a look at an example using that idea. Two similar, that's important that we know that, two similar spheres have circumferences in the ratio 2 to 5. Given the volume of the smaller sphere is 48 pi cubic centimeters, or centimeters cubed, what is the volume of the larger sphere? Now, notice I'm not underlining or highlighting the word sphere because it doesn't really matter what the object is. A sphere is a ball, but it doesn't matter. We can still do this without knowing that. That they're similar is very important. That we're given circumferences. Circumference is a length. That's very important. And that ratio is 2 to 5. So our scale factor, it's important to know, is 2 to 5. That's the ratio of the lengths, the circumferences. Given the volume of the smaller sphere, what's the volume of the larger sphere? Well, remember the ratio of the volumes will be the scale factor cubed. So 2 cubed and 5 cubed. 2 cubed is 8, 5 cubed is 125. There's the ratio of the volumes. Now let's make a proportion with the volumes that we know and want to know and the ratio of the volumes. So the smaller sphere has a volume of 48 pi. 48 pi. The larger sphere, we don't know the volume. What is it? So we can say V for volume, or X if you prefer that, equals the ratio of the volumes, 8 over 125. And then we can cross multiply to solve. 8 times V, 8V. 48 pi times 125. I'm just going to write it like that, 48 pi times 125. Now, why write it like that? Because I don't need to pull out a calculator then. And now when I divide by 8, you'll see some easy math going on. 8 into 48 goes 6 times. Now all I have to do is multiply 6 times 125. So the volume that I need, that larger sphere, is 6 times 125 and then times pi, or 750 pi centimeters cubed. We did it! So let's review. If we're comparing ratios for similar figures, now remember that's a really important thing. These are for similar figures. The ratios for similar figures. The corresponding lengths, that's just one dimension. The exponent is 1. The ratio of areas is squared. That's 2 dimensions. 1 dimension, area is 2 dimension, volume is 3 dimension. So the corresponding lengths, that's the same as our scale factor. The ratio of the areas, that's just our scale factor squared. And the volumes is our scale factor cubed. If it says area, we square it. If it says volume, we cube it. And basically, if it says anything else, so let's just call this everything else, meaning not area and not volume, then it's just the scale factor. So area gets squared, volume gets cubed, everything else is the same as the scale factor. So take a look at some examples. 2 to 5 will be the ratio of the corresponding lengths. Going this way, to areas, we have to square those. 2 squared and 5 squared, which makes 4 to 25. That's the ratio of the areas. To get the ratio of the volumes, scale factor cubed. 2 cubed, 5 cubed makes 8 to 125. How do we go from area if we start here? First, let's go back to scale factor. So if these are numbers squared, how do I make them not squared? By doing the square root. Square root of 9, square root of 4, that makes 3 to 2. The scale factor is 3 to 2. Now how do I get to volumes? 3 cubed, 2 cubed makes 27 to 8. How do I get from volume? Always go back to the first dimension, scale factor. So if going from squared to not squared is square root, going from cubed to not cubed is cubed root. Cubed root of 8 and cubed root of 125. Pull out your calculator and see how to do that. Here's my calculator. Go to the math button. Find cubed root. It's the fourth choice. So select 4 or scroll down to find it. Then type the number in the cubed root. Cubed root of 8, enter. Let's do it again for cubed root, fourth choice. Scroll down or choose 4, and then 125, enter. 5. So we know the ratio 2 to 5. Now to areas, 2 squared to 5 squared, 4 to 25. Not too bad, right? Let's take one example where we're using the relationship of the ratios. Some information about the volumes and surface areas of two similar prisms is given. Prism A's volume is 54 cubic feet. Prism B's volume is 16 cubic feet, and its surface area is 12 square feet. Find the surface area of Prism A. Well, notice how we're given a volume of the first one and a volume of the second one. Let's use those volumes to get a ratio. 54 over 16. First thing we're going to do is simplify that. 27 over 8. Now we're going to figure out the cubed root, and we're not going to say equals. Cubed root of 27 and the cubed root of 8. Well, we did that earlier. Cubed root of 27 is 3, cubed root of 8 is 2. So the scale factor, which we always want to get to first, is 3 over 2. Now, since they wanted area, the area of the first guy is 12. The area of B, prism B, is 12. The area of prism A, we don't know. So let's go to the area ratio. The areas, take our scale factor, square it. 9 to 4. Now we can make a ratio or a proportion with that ratio. 9 to 4, and then the area of prism B is 12. The area of prism A, we don't know it. So let's call it A. So notice so far that we were putting A on the top, B on the bottom. Prism A, prism B. That was the order where we started. Now let's cross multiply to solve. A times 4, 4A, 9 times 12. I just like to write it like that because now when I divide by 4, 12 divided by 4 makes 3, and 3 times 9 is 27. So without pulling out my calculator, I know the area for prism A is 27 square feet. We did it! For a summary, take a few minutes to explain the relationship between areas, volume, and everything else of similar figures. See you in class!